In this video, we will solve a numerical example on cost minimization. The question is, a producer desires to minimize the cost of production. C is equal to 4K plus 2L, where K and L denote the units of labor and capital are employed respectively, subject to the production function Q is equal to 8 times K to the power 1 upon 2 times L to the power 1 upon 4. Find the equilibrium combination of capital and labor in order to minimize the cost of production when the output level is 60 units. Okay. So this is a case of cost minimization. So our endeavor is to minimize C, which is cost, which is equal to 4. 4 denotes the price of capital, plus 2 denotes the price of labor, that is the wage rate. So we want to minimize the cost subject to the production constraint that we are facing, that is 8 K to the power 1 upon 2 times L to the power 1 upon 4, and it should be equal to Q, and we have the production constraint, that is we want to produce 60 units of output. Okay, so the question is, we want to minimize the cost to produce 60 units of output when we have this production function. So there are two ways to solve this question. First is the Lagrangian multiplier method, and another is the tangency condition. Let us first solve it using Lagrangian multiplier method. So for that, what we need to do, we need to to solve it using Lagrangian multiplier method, we set the production constraint, this equation equal to 0. That means we have 60 minus 8 K to the power 1 upon 2 times L to the power 1 upon 4. We set it equal to 0. Okay, first step is this. Second step is we multiply this resulting constraint both sides by lambda. Okay, so lambda times 0 will be 0 on the right hand side. I will not write it. Now then the third step is we form the Lagrangian function, which is equal to the objective function, which is our cost function, and the resulting constant that we have formed. So it will be equal to 4K plus 2L plus this equation, lambda times uh, 60 minus 8 K to the power 1 upon 2 times L to the power 1 upon 4. This is our Lagrangian function. Okay, to find out the optimal combination of capital, labor and lambda. So lambda denotes the shadow price. I will not explain the lambda here. So since our endeavor is to find out the optimal combination of capital and labor, we will concentrate on that very thing. So to find out the optimal values of K, L and lambda, we differentiate this Lagrangian function partially with respect to capital, labor and lambda, and set them equal to 0 simultaneously. So let us see. So L subscript L. Okay, so let me write. Let us say it denotes the partial derivative of this function with respect to L. So derivative of a constant is, since we are taking partial with respect to L, derivative of first term is 0 because here we have K. Derivative of the second term is 1. We are left with 2 because the derivative of L is 1. Then we have here plus this term. So the derivative of 60, it is constant, it is derivative 0. Now we need to find out the derivative of L here. So the exponent of L becomes coefficient. So we have and we have minus, obviously. So we have minus, then we have lambda, then we have the exponent of L is 1 upon 4, which becomes coefficient. Then we have 8 K to the power 1 upon 2, it remains the same, and the exponent of L is subtracted by 1. So 1 upon 4 minus 1 is equal to, so it is 1 minus 4, which is minus 3 upon 4. Okay, and we set it equal to 0. Likewise, we take the derivative with respect to K partially. So differentiating partially with respect to K, derivative of K is 1. We are left with 4. Then we have minus, then we have lambda, and we partially differentiate this with respect to K this time. Okay, so the exponent becomes coefficient. So we have 8 times 1 upon 2 K to the power, exponent is subtracted by 1, so it becomes minus 1 upon 2 L raised power 1 upon 4 remains same because we are taking partials with respect to k this time, and we set it equal to 0. Okay, so let us take only these two. These are suffice to find out the value of capital and labor here. Okay, so we do one thing here. Since this term is equal to 0, this term is also equal to 0, can we rewrite these two as, where do I write? I don't have the space here, so let me rewrite these two equations. So can I write 2 is equal to lambda, so 4 ones are 4 twos are, I get here 2 k to the power 1 upon 2 L to the power minus 3 upon 4, and if I rewrite it, it will become 4 is equal to, so here 2 ones are 2 fours are, here we will get 4 k to the power minus 1 upon 2 L to the power 1 upon 4. Okay, then what will we do? Let us say this is equation first, this is equation second. We divide equation first with equation second. Okay, so to save the space, I divide them here. I divide it here. So 2 upon 4 is 1 upon 2 is equal to lambda lambda cancel. So 2 ones are 2 twos are, here we get 1 upon 2. Transpose this k to numerator, it will get multiplied, so it will become k to the power 1 upon 2. Transpose it here, it gets multiplied, but exponent sign changes. It is minus upon 1 upon 2, it becomes plus 1 upon 2. Okay, in the same way we have L raised power 1 upon 4 here. Transpose this term here, it gets multiplied, but exponential sign changes. So these are the basic things, so it becomes plus 3 upon 4. Bases are same, we can add the exponent, so it becomes k 1 upon 2 plus 1 upon 2, and in the denominator again bases are same, we have 1 upon 4 plus 3 upon 4, which is equal to, so 1 half plus 1 half is 1, and here 1 upon 4 plus 3 upon 4 is 4 upon 4, which is L. Okay, so we got here k upon L when I solve this very much. Okay, I guess so. This 1 upon 2 gets cancelled on both sides, which implies k will be equal to L. Now we plug k is equal to L into the production constraint. Okay, so we have 8 in place of k I write L, so we have L raised power 1 upon 2, then we have L raised power 1 upon 4 is equal to 60. So again bases are same, we can add the exponent, so we have 8. So 1 upon 2 plus 1 upon 4 becomes 4 plus 2 divided by 8, so it becomes 10 divided by 6 divided by 8. So I'm really sorry for this slow calculation. So we have 4 plus 2 is 6, and 2 4s are 8, 6 upon 8, which is equal to 2 3s are 2 4s are, so we get 3 upon 4. Okay, so L raised power 3 upon 4 is equal to 60, which gives us L raised power 3 upon 4 is equal to 60 divided by 8, or L is equal to, transpose it here, it becomes 60 divided by 8. So let us see what is 60 divided by 8 first. So 60 divided by 8 is equal to, so 2 30s are 2 4s are, okay, then we have 2 15s are 2 2s are, so 15 divided by 2, 15 divided by 2, when I transpose it becomes 4 upon 3. Okay, so L will be equal to 15 divided by 2 raised power 4 upon 3. This will be the optimal choice of labor employed to minimize the cost. To find out the value of k, plug k is equal to L in this equation. So since k is equal to L, that means k will be equal to, k is equal to again 15 upon 2 raised power 4 upon 3. So L star k star, that is optimal combination choice, will be 15 upon 2 4 upon 3 and 15 upon 2 4 upon 3. Okay, this will be our optimal choice. I hope I have done the calculation correctly. Okay, so this should be the answer. Now let us solve it by another method, or rather what we call the tangency condition. Okay, so for that what we need to do, let us rub this out, and to see whether we have done it correctly or not, we check it using tangency condition. So for that what we do, let us draw the graph to make the things clear. So if I draw the graph here, a simple graph, we have the labor on the horizontal axis, units of capital on the vertical axis. We have the production constant. Okay, so this is our ISO count. Okay, with the given ISO count we want to minimize the cost. Okay, let us say this is our one ISO cost line. Okay, so another can be this one, then we have another. Okay, so the consumer's endeavor is to minimize the cost subject to the given production constant. Okay, so the optimal choice will not be, let us say this is IC1, IC2, and this is IC, rather we don't have the indifference curve here, we have ISO count. Let us say IQ1, IQ2, and IQ3. Okay, now which of these will give us the optimal choice? Optimal choice will lie at a point where the ISO count and ISO cost lines are tangent to each other. So this point will give us the optimal combination. This point satisfies a condition where the marginal rate of technical substitution between labor and capital is equal to the input prices, that is price of labor upon price of capital. Okay, now using tangency condition, our equilibrium will be at a point where marginal rate of technical substitution between labor and capital is equal to ratio of the prices, that is price of labor upon price of capital. Now what is price of labor? Price of labor is 2, price of capital is 4. Okay, marginal rate of technical substitution is simply the ratio of the marginal product of labor and marginal product of capital, and it should be equal to PL upon PK is 2 upon 4. So MPL is simply the change in the output due to the change in the units of labor employed. MPK is the change in the output due to the change in the units of capital employed, and it should be equal to 2 upon 4, which is equal to 1 upon 2. Okay, now the partial derivative of production function, this production function with respect to labor. Okay, so we need to partially differentiate this with respect to labor. So the exponent of L becomes coefficient, so we have 1 upon 4, then we have 8, then we have k to the power 1 upon 2. It remains the same because we are taking partials with respect to L, but the exponent of L gets subtracted, so 1 upon 4 minus 1 is minus 3 upon 4. Likewise, we take partial with respect to k, so exponent of k becomes coefficient, then we have 8, k to the power, exponent is subtracted by 1, it becomes 1 upon 2, and L to the power 1 upon 4 remains the same because we are taking partial with respect to capital, should be equal to 1 upon 2. So 8 and 8 gets cancelled, we are left here 1 upon 4 into transpose here, it becomes 2 upon 1. Again transpose this to numerator and this to denominator, it will become k upon L is equal to 1 upon 2. So here we have 2 upon 4, k upon L is equal to 1 upon 2. So 2 upon 4 is basically rather 1 upon 2. So 1 upon 2 and 1 upon 2 will get again cancelled. So k upon L is equal to 1, which implies k is equal to L. Now plug k is equal to L into the production constant. So we have 8 times, in place of k we write L raised power 1 upon 2, and in place of L we have L raised power 1 upon 4, same, is equal to 60. Again we have 8, so 1 upon 2 plus 1 upon 4, शामत मुश्ती को be 1 upon 2 plus 1 upon 4, so 6 divided by 8, so it becomes L raised power 6 divided by 8 is equal to 60, or L raised power, so this is 2 3s are 2 4s are is equal to 60 divided by 8, which is equal to 15 divided by 2. So L will be equal to, transposing the exponent gets reciprocated. Okay, so we have 15 upon 2. If it is here 3 upon 4, it becomes 4 upon 3. And this is the optimal units of labor employed. So K will be equal to L, since they are equal. So we have 15 upon 2 raised power 4 upon 3. That will be the units of capital employed to minimize the cost. I hope I make myself clear in this video. You find out this video helpful. Thank you.